In this video, we're going to look at an example of using the log rule for integration when we use a u-substitution first in order to simplify the denominator. So here I've got the integral of x over x plus 1 squared. And if we expanded the x plus 1 squared, we would have three terms in the denominator. And the problem is, essentially this is the problem. If you have a over b plus c, you can't break it up like this, a over b plus a over c. You can try to break it apart different ways, but it doesn't easily break apart like this. But if you have something that looks like b plus c over a, you can easily rewrite it as b over a plus c over a using the common denominator. So sometimes when you have multiple terms in the denominator, what you want to look at is see if you can use a u-substitution that gives you a single term in the denominator, and then use that substitution to rewrite the numerator and then break it apart into individual fractions. So here, expanded, the denominator would have three terms. So a u-substitution, u equals x plus 1, might help us out. In general, this wouldn't be a good u-substitution because du dx, when we take the derivative with respect to x of both sides, we get du dx equals 1, which doesn't differ from the numerator by just a constant. So 19 times out of 20, this is a bad u-substitution. But in this case, it's worth trying to see if it will simplify the denominator in such a way that lets us break it apart. So I see from this that du equals dx, and the other thing I see from this is subtracting 1 from both sides of this expression. I see that u minus 1 is the same as x. So I can step over now to my integral and see if this helps me out at all. So I'm going to replace x with u minus 1. So my numerator has a u minus 1. And I'm going to replace my denominator, x plus 1 quantity squared, with u squared. And then du and dx are equivalent, so I can replace the dx with du. And now I have two terms in the numerator that aren't connected with a squaring or some other power. And I have a single term in the denominator, so this is going to allow me to rewrite this integral as u over u squared minus 1 over u squared du, which can be written as the integral of u over u squared can simplify to 1 over u, minus, and 1 over u squared is the same as u to the negative 2 power du. And now I can integrate. The antiderivative of 1 over u is just going to be the natural log of the absolute value of u, based on the work that we've been doing so far, minus, now I have what looks like a power rule type of a scenario. So instead of decreasing the exponent by 1, I'm going to increase the exponent by 1. So negative 2, that's what happens when we work backwards. So negative 2 plus 1 is negative 1. And then I need to multiply by the reciprocal of negative 1, which is actually just negative 1. And then plus a constant of integration. And then I can simplify things. I get the natural log of the absolute value of u, but u is just x plus 1. And this is going to be minus parentheses. I get a double negation sitting right here, negative, and a minus is going to give me a plusy. So it's going to be plus u to the negative first, and u gets replaced with x plus 1 to the negative first. And then if I wanted to, I could rewrite this without the negative exponent, although I don't think there's any real reason for doing that. I could, if I wanted to, if I had a good reason for doing it, I could rewrite this as the natural log of x plus 1 plus 1 over x plus 1 plus c. And I could get common denominator and combine things if I had a good reason for doing it. In this case, I think this is good enough. In fact, I think this is good enough. In general, I think having a negative exponent's perfectly fine. We can always change that if we have a specific reason for doing so.